the area under a curve f of x, which is non-negative and continuous on A and B. So this is A and this is B on the x-axis, y-axis. So one way to do this is to draw rectangles, and in this case we've used the left hand side of the rectangle to form the vertex which touches the curve. So in this case we have 1, 2, 3, 4 rectangles, and each has a width of delta x, where n is the number of rectangles. Then delta x equals b minus a over n. So the width delta x is given by this total length of the 4 rectangles divided by the number of rectangles. So now if we label this first line, which touches the curve, as x0, this one as x1, x2, x3. The last line in this will be xn minus 1, because we're considering this side of the rectangle. So the last line we're going to consider in the height of the rectangle is going to be xn minus 1. So the area is given by f of x0, which would be that height, times the width, which is delta x, plus f x1 delta x plus f x2 delta x, carries on until we reach f xn minus 1 delta x. We can sum this up in something called a Riemann sum, which is Rn, and this would equal the sum of where I equals 0 to n minus 1. So we're starting off here at 0 and we're going to finish at n minus 1 f of xi delta x. So all this replaces this whole calculation. So we take this from expression and substitute I from 0 to n minus 1, and then add them all up, and that will give us the area. Now this is an estimated area. If we want a more accurate area, what we have to do is then take more rectangles. So we would split these further and the area as a limit as n tends to infinity would give us an accurate area. This is called the left-hand sum, because we're taking the left hand of the rectangle to be the length of the rectangle, or y. In this case of estimating the area under a curve, we're going to take again rectangles, but the right hand side of the rectangle touches the curve, and then we work out the area of the rectangle to estimate the area. Again, we have in this case 4 rectangles of width delta x. So this is delta x along the x and y axis, and here we have a curve f of x which is non-negative and continuous on A and B. Here we label this as x0, x1, x2, x3 and so on. But in this case we start off at f of x equals 1, so area equals f x1 delta x plus f x2 delta x, and then so on until f xn delta x. Again, delta x is given by b minus a over the number of rectangles, which is n. If we now represent this as a Riemann sum, so Rn equals the sum from I equals 1 to n f and x delta x. So this represents this whole sum that we have to do, and again this is called a right hand sum. And it gives an estimate of the area under the curve. If we want a more accurate area, what we have to do is increase the number of rectangles, and as the number of rectangles, as n, the number of rectangles tends to infinity, we get an accurate area. So the area as the limit n goes to infinity, we get more accurate area. When we integrate, we have the integral of b a f of x. This in fact is the limit as n tends to infinity of the sum of n minus 1 for the left-hand sum I equals 0 f xi delta x. So when we take the integral of the function between the upper limit b and take away the integral of the lower limit a, we get an accurate area under the graph. Another way of estimating the area under a curve is to use the midpoint sum, and this essentially is the same except we use the midpoints of x1 and x0, etc. So again, delta x equals b minus a over n. So this is a, this is b, and n equals number of rectangles. This is f of x. Here we have x0, x1, x2, x3. And what we use is the midpoint formula, which is, midpoint formula is L1 plus R1 over 2. So it's the left hand side plus the right hand side divided by 2, and we substitute that into our formula. So we would get area equals delta x f x1 plus f x2, etc. And this would go on to f xn. And for these values we don't use x1 and x2, we actually use the midpoint formula to work out these points here. So say we had delta x equals 1, so we'd make a number line 1, 2, 3, and then work out the midpoint here. So this one would be 1.5, 2.5, 3.5. And then we'd substitute this into the formula. So delta x, so the Riemann sum would equal, say, a delta x of 1 for here would equal f of 1.5, which is 3 over 2, plus f 5 over 2, plus f 7 over 2, and so on. And this would give us a very good estimate of the area under the curve. Sometimes when we can't integrate to find, or do a definite integral to find the area under a curve, we can estimate or make a very good estimate of the area under a curve using trapezoids. So what we do is from A to B underneath the curve f of x, we draw trapeziums. So this would be 1, 2, 3, and so forth. And that gives us a very good estimate when we add up the area of the strips, which are trapeziums underneath the curve. So this gives us a very good estimate of the area. The trapezoid rule I'm going to write out in words because sometimes it's easier to understand. So the integral from b to a f of x is the area, and then we get an estimate. Each width has to be the same for these strips, or these trapezoids. So we have the width of the strip, and we divide that by 2. The width of the strip is given by delta x, or h, sometimes called h in some textbooks, is b minus a over n, where n is the number of strips. Okay, so back to the trapezoid rule. So it's the width of the strip divided by 2, and then we multiply this by the first height plus the last height plus 2 times the middle heights. So what do we mean by height? By height we mean y, which is this here. So this would be the height, which would be y, or f of x. So what do we do here? What we need to do is we need to get the width. So we get first of all delta x, or h, and that would give us the width, which is b minus a over n. Then we need to make a table, and on the table we put a as x0, then the edge of the first strip x1, x2, x3. So this would be, the first one would be a, the x1 would be a plus the width that we found here, delta x. Then the next one would be x1 plus delta x. The next one would be x2 plus delta x. So we make a table of x0, x1, x2, x3, etc. until we get to b. Then what we need to do is, for these numbers that we've worked out, x1, x2, x3, we need to put them into our f of x. So we need f of x0, f of x1, f of x2. And then that would be the first height. What we work out right at the end for b, that would be our last height. And then anything in between x1, x2, x3, those would be our middle height. We plug them into our trapezoid rule, and that is an estimate of the area. Let's have a look at using the trapezoid rule. And we're going to estimate the integral of 2 to minus 1 dx 2 plus x squared, where the number of strips is 6. So first of all, we have to work out the width of each strip. So we make a number line from 1 to 2, so we have a 0, -1, 1, 2, and then we need to divide this into 6 strips. So we have 1, 2, 3 to begin with, so we're going to have to divide each one of these into half to give us 6 strips. So divide the range -1 to 2 into 6. Now the width of each strip, like I said, it can be called x or delta x or h. We call it delta x in this case, is given by 2, which is b, minus a, which is -1, all over n, which is the number of strips, which is 6. So this equals 3 over 6, which is a half. So that's the width of the strips. Now we want to work out our x1, x2, x3 values. So we start off at x0, x1, x2, x3, x4. So we're going to have 1, 2, 3, 4, 5, 6, 7. x4. So that's 0, 1, 2, 3, 4, 5, 6. Sorry. 4, x5 and x6. So those are going to be our values. Now let's put in -1 into our equation. No, sorry, this first of all we're going to work out what these values on the x-axis are. So x0 will be -1. At x1 here, it'll be -1 plus a half, which is -1/2. At x2, which is here, it'll be -1/2 plus a half, which is 1. x3 will be a half. x4 will be 1. x5 will be 1.5, and x6 will be 2. So those are our x values. Now we plug in our x values into our equation and apply our trapezoid rule. So the trapezoid rule says it's the width, which we said was a half, divided by 2. Then we have our first f of x, so that would be -1. So that's 1 over 2 plus -1 squared, plus our last value, which would be x6, which would be 1 over 2 plus 6 squared, and then plus 2, and then all our middle values. So we've done that one, and we've done this one, and now we're just left with our middle values. So it would be 1 over 2 plus -1/2 squared, plus 1 over 2 plus 1 squared, plus 1 over 2 plus 1/2 squared, plus 1 over again 1 squared, so that's 2 plus 1 squared, and then the last one plus 1 over 2 plus, sorry I got mixed up with my brackets there, 2 plus 3 over 2 squared, and then we end the brackets, and that would give us an estimate of our area. Simpsons rule, or Simpsons 1/3 rule, gives us a very good estimate of the area under a curve if we can't do a definite integration. So if we have a y and an x-axis, a curve f of x, Simpsons rule uses parabolas over 2 intervals, so it would be like this, like that, like that, like that. So over 2 intervals. And if we write it in words, the rule, so we have the integral from b to a of f of x. So this is the area, and the rule says if we apply the rule, we get an approximation of the area. So we get the width of the strip, which is given by delta x, which is the width, equals b minus a over n, which is the number of strips. So this would be A and this would be B. So width of the strip, the 1/3 rule, so we divide by 3 and then we multiply by the first height plus the last height plus 2 times the even heights plus 4 times the odd heights. And that would give us a very good estimate of the area under the curve. What do we mean by height? So if this was x1, x2, x3, we simply apply our width formula. So the first width, the first x1 would be a plus our width that we got from this delta x, so it would be a plus delta x. Then the next x2, that would be x1. So x of 2 would be x of 1 plus delta x, and so on. Then the answer that we get here, we plug into our f of x formula or our integral formula, and we get the heights, or the y. Plug that into our Simpsons rule and we get a very good estimate of the area. Okay, if we have a function over 2 intervals, there are several ways we can estimate the area. If we use the left-hand sum rule and rectangles, we can see we get something like this underneath and going above the curve f of x. So that's not very good. If we use the trapezoid rule, then we can sort of draw trapeziums underneath. and there, which gives us a better estimate. And with Simpsons 1/3 rule, what we use is a parabola. Say going over these two intervals, we would have a parabola going through there and like that. So Simpsons rule uses two intervals for a parabola. And this is an estimate, or a very good estimate, of the area. If we had a function f of x equals f of x equals 5x e to the minus 2x, and we wanted to estimate the area underneath that, we'd have to integrate between the limits that we're told 1.3 and 0.1, 5x e to the minus 2x dx. So this is our upper limit and this is our lower limit. So we can think of this as b and this as a. The width delta x, or sometimes called h, is b minus a over the number of intervals, which in this case is 2. So this would be 1.3 minus 0.1 divided by 2, which is 0.6. Then we use our Simpsons rule, so it's the width 0.6, so this would be the integral of 1.3 0.1 5x e to the minus 2x. The area would be approximately the width 0.6 divided by 3, because it's Simpsons 1/3 rule. Then we have the first height, which would be given by f of 0.1. The last height, which is f of 1.3. And then because this middle height is an odd number, we do 4 multiplied by the middle height, which would be 0.1 plus 1.3 divided by 2. And that would give us an estimate of the area. The definite integral is used to find the area bounded by the curve. And the x-axis. So if we have a curve, this would be x, this would be y, and we have a curve f, y equals f of x, and it's continuous along a and b, so this would be a and b along the x-axis. Then if we draw, as we previously discussed, a rectangle and try to estimate the area using rectangles and call the width dx and the height y. So the rectangle, or the rectangles that we draw, area equals dx y, and if dx tends to 0, we have a better area estimation. So this means that as this dx or delta x gets smaller and smaller, we get more and more rectangles underneath this area bounded by the curve and between B and A, and we get a very, very good estimate of the area. So the area then, if we do a sum notation, area equals the sum of x from A to x equals B y dx, or area of the limit as x tends to 0, the sum of x equals A, x equals B y dx. And this is the same as the integral b to a y dx. When we write this integral sign, it really means like the sum of all the little rectangles. So we can just do y dx from b, which is the upper limit, to a, which is the lower limit. So let's do an application. So if we had y equals 2x between the limits 0 and 4, and we wanted to work out this area here. So how would we do that? So the area equals the integral between 4 and 0 of y equals 2x, which is 2x dx. So what we do is we integrate now. So the integral of 2x is 2x squared over 2. Now we have to apply the upper and lower limits. So this equals x squared. So a equals x squared. And we can either draw brackets like this and write 4, 0, or we can write the x squared and a line with 4, 0. And what this means is wherever we see an x, first of all we put the upper limit for x and apply the function, and minus the lower limit. So this would become, we put in the upper limit for x, so this would be 4 squared, and then minus, put in the 0, so 0 squared, and this is 16 units squared.